Okay, so for today's problem, we're looking at a torsion pendulum consisting of a non-uniform disk suspended by a wire whose torsion constant is 0.033 Newton meters per rad. The torsion pendulum undergoes simple harmonic motion with frequency of 1.59 Hertz, and at a time of 0, the angular position is negative 0.518 radians, and the angular velocity is 3.02 radians per second. The torsion constant is 0.033 Newton meters per rad. So we're first asked in part A to find the rotational inertia of the disk uh, about its suspension axis. And this in and of itself is relatively simple because we have a few equations we can go off of here first. So we know simply that frequency is equal to 1 over t, and using simple rearranging we can find that t is equal to 1 over f. And this is going to come in handy because we also know for torsion pendulums that t is equal to 2 pi square root 1 or sorry, not 1, moment inertia over our torsion constant. So some simple rearranging, we can do 1 over f, which in this case is our 1.59 hertz, equal to 2 pi square root I over 0.033. And with some simple rearranging, we eventually find that I is equal to 3.306 times 10 to the negative 4, just like that. Alright, so that's simple enough, and that's going to come in handy later on when we move on to part B, in which we're supposed to determine the amplitude, angular frequency, and the phase shift of the motion that was earlier described. So, this one's a bit trickier, but we can start simply with what we know. We know that our, let me see here, sorry about this, angular frequency is equal to 2 pi over over our period, which we already found earlier. We found that to be 1 over our frequency. So we can do some simple arranging, finding that 2 pi is equal to 0.629 9.99 rads per second. And that's the easy part. Now we've got to find a way to, and just bear with me here, I'm going to erase this stuff to make room. We've got to find a way to model this here. This is the equation we can use to model just about everything that we need. So we're going to have to start by breaking this up into different components. So we can first write out what we know. We know that at 0, we have the equation modeled in this manner. T is equal to 0, so it's simply cos of phi, and we find that 0, it's listed as being at 0.518 radians. So that is our equation 1. Now, for our equation 2, we take the derivative of this to find the velocity. Now, that is modeled in this manner. V of t equals this here. Plus theta. And we plug in what we know. We know that it is equal to 3.02 rads per second. And we know already our angular frequency, which we found earlier to be 9.99. We do not know our theta max, and we know that this is t equals 0, so it's just sine of phi. So let's rearrange this here for the variable we want. Theta max is equal to 0.518 negative of that over cos phi. And now we can take this and sub it into our second equation here and write that as 3.02 equals negative 9.99 times negative 0.518 over cos phi times sine phi. And the sum rearranging, we find that 3.02 over negative 9.99, that over 0.518 is equal to sine phi. Oh, hold on a sec, I forgot the negative here. It's equal to sine phi over cos phi, which, if you know basic trigonometry, is equal to tan phi. And from there, we can, just going to erase some of this stuff up top here. We can take tan, or inverse rather, of the number we've just computed here. Bear with me here, I have this written somewhere. Yes, 0.584 is equal to phi, which means that phi equals, and this is the kicker, 0.528 or pi minus 0.528 because of cast rule, which states that it's either here or here. So if I go ahead and get rid of this, we can determine which is the correct one. Now we know according to equation 1, negative 0.518 equals pi m cos phi. So we can find that since this is negative, cos subsequently would be negative. So the one in quadrant 2 is the correct one. So phi equals 2.613 rads, because that is what pi minus that equals. And from there, it's relatively simple. We can find our amplitude by simply doing 0.518, which is an equation we found earlier on, over cos phi, which is equal to 0.5998 radians. And from there, we've got all of our data. We can simply write out the final equation. So, that would look as follows. Times amplitude, cos, angular frequency times phi, plus phi. We plug in our solid variables now. Our amplitude, 0.5998 times cos, our angular frequency, which is 9.99, t, plus our phi, which is 2.613, And now let's worry about significant digits. Simplify this a bit. And we find that this is equivalent to 0.600 cos. That's already correct. Plus 2.61. And that is our equation for part B. Now, that's out of the way. Let's make some room for the next part, in which we have to find the total mechanical energy. Now, this is pretty simple, because if you know how energy works, you know that energy mechanical is the sum of the energy in the system. And we know that we can model these two parts individually, but we don't even need to do that, because this would be modeling it in such a manner that it would be E at any given time, being able to break it up into these parts. We're only interested in the whole part, so we don't need to worry about breaking it down to individual ones. We'll just pick a max of either or. And quite simply, we can do this for the total potential energy, which is modeled in half times our torsion pendulum constant times theta. But in this case, since we're doing it maximum potential energy, actually no, apologies, this would be kinetic. No, no, this would be potential. Sorry about that. We have to have the max possible value for this here. So that just so happens to equal our amplitude, which we solved earlier. So energy mechanical is equal to half our torsion constant, which is 0.033, times our amplitude, which we found to be 0.5998. Square that. Our energy ends up equaling 0.0594 joules. And for the last part here, rather simple one. If the disk was replaced by an object with double the moment inertia about the suspension axis, how would this affect the frequency? This is rather simple if you think about it as we showed before. Since period is equal to 1 over f and also equal to 2 pi square root moment inertia over k, if you simply double this, set these equal to each other here. If you simply double this and you run through it, you'll eventually find that the frequency would decrease. And that is all for the first question.